Okay, so hello to anyone still watching. um, yeah, so this is again a re-recording of one of the lectures I gave, which unfortunately the recording just doesn't exist. So I'm re-recording this without an audience. I'll try and remember some of the interesting questions people asked during the live talk, and I'll apologize. This video is a little bit late. I too got swamped with work and examinations, so I thought I'd get that done first before finishing off the video series. So, where were we? So in the first video, I talked about the trigonometric functions. I defined them, we defined them using right triangles, and with a little bit of creativity, we could apply the trig functions to any number of triangles. We did a bit of study there, and we looked at the geometry. In fact, to begin with, we were looking at notions of lengths and angles, but we eventually generalized to area. Not really generalized, but eventually we studied areas using sectors, segments, areas of circles and triangles, etc. And I ended that video with a kind of what we could do in terms of generalizing the trig functions to the unit circle. And then the video previous to this one, we looked at graphing. So we looked at what the sine function looks like, the cosine function, the tangent. In fact, we introduced a variety of different trig functions. For that video, I wanted to review functions for those that may not be super familiar with some terminology I might be using. Although on review, I might have gone a bit too in-depth, considering some aspects are definite prerequisites for this, trigonometry. And other aspects you don't really need to know until later on. But I digress. So we now have a notion of what these graphs look like, and graphing is a nice in-between the geometric section, which we did in the first video, and this algebraic section, which we're going to be discussing today. So why do I say algebra? I'm going to ramble a bit in these first 5 minutes, so I do apologize, but I feel it's important. So if you ask, I think someone in high school what algebra is, quite often they'll just say using letters to represent numbers. So x equals 2, and maybe you have equations like y squared equals 4, and you may have to solve it for different values of y. And that's what their answer would be to the question, what is algebra? And it's not wrong. I mean, algebra has using letters for numbers is a big part of algebra, but really and truthfully what algebra is about having these sort of mathematical objects, and in this case, or in earlier cases, we look at numbers. So you could have sort of whole numbers like 4, 2, 1, 60. You may have fractions, and so this is another kind of bit of maths which often people see as separate to just whole numbers. And you may have real numbers, so this could be things like decimals, or things like pi, or e, or the square root of square root of 2, etc. And you use letters, well, you got these mathematical objects, these numbers, and we look at operations which we can use on these numbers. So in this case, we kind of have like addition and multiplication. And we may look at subtraction, but we've got to be careful if we go into the negatives. If we go into the negatives, then we need to introduce negative numbers, I guess. But division isn't always defined. I mean, if you want to stay in the whole numbers, 4 divided by 3, it doesn't work. You're suddenly out of the whole numbers, or in this case, the integers. And similarly over here, I mean, we look at operations such as addition, multiplication, subtraction, and division. And we can do the same with these sort of decimals, if you will, though in this case I've written them as their constants. And the reason why we use letters, right, instead of just lots and lots of examples, is because by using letters instead of numbers, we can emphasize properties of these objects. So here we may do a plus b, but there's something nice about this, is it's the same as b plus a. And this isn't just true for some examples like 1 or 2 or 4. This is true for all integers, right? You can swap them, they commute over the plus symbol. And that's the advantage of algebra, is that we don't look at specific examples, but in fact we abstract our focus to all possible examples by using letters instead of numbers. And we do this because then we can study the operations on these objects. So when I say that in this section we'll be studying algebra, really and truthfully, instead of numbers, our objects are going to be the trig functions themselves, and we're going to be looking at some basic trigonometric identities. So this is a notion of two trig functions being equal, because you can set sine of theta is equal to cosine theta, and you can try and find values of theta such this is true. But the fact is, when I write this sort of 3 lines instead of the 2 lines, this means that these are equal in terms of functions, which just isn't true. We can find values which these functions are not equal. So equations, where you just have this equality, are true for particular values of your input, but identities are true for all the input. So these functions, in order to be identical, need to be equal for every possible value. Now this may seem a little bit complicated at first. I sort of approached this from quite an abstract perspective, but we've actually seen some identities throughout these last couple of videos. I mean, we know that the tangent of any value, any angle, is identical to the sine of any angle divided by the cosine. And by definition, our secant and cosecant and cotangent are equal to sort of 1 over the cosine of any angle, or 1 over the sine of any angle, or 1 over the tangent of any angle, provided they're defined. I mean, if we don't want this to be divided by 0, but that's fine because the secant isn't defined for when the angle is such that cosine is 0. So that this all makes sense. So what we want to look at in this video is some properties or some identities we can look at in terms of trig functions. So the first one's called the Pythagorean identity, and this is because it is literally Pythagoras. A squared plus b squared equals c squared for a right triangle. Well, we can think about a right triangle. In fact, for any kind of sort of any coordinate, which would be sort of cosine and then sine. Here, a right triangle, our C is 1. Our A would be our height sine. So this is sort of sine of our angle, and often it's conventional to when we write a function with our argument here, is to write our powers beforehand. And this just gets rid of any ambiguity in case we want to omit our brackets. So we could write sine in brackets and then end it here. Or we could write sine squared and then have our brackets and then put the angle here. But if you don't want to write the brackets, then this doesn't really make sense, because does this mean you're taking the sine of the angle squared, or does this mean you're squaring the whole trig function? So often it's conventional to write our exponent before the argument, just to emphasize that we're not squaring the angle. But I digress. So yeah, we can just apply Pythagorean theorem to this triangle, which means sine squared theta plus cosine squared theta is equal to 1 squared theta, and this gives us our Pythagorean identity. And this Pythagorean identity holds for sort of any point on the circle, which means it holds for any angle between sort of, well, you can think of it between 0 or 360 degrees, or 0 and 2 pi radians, but this actually holds true for any number of rotations, because that's how we generalize the trig functions. So let's look at this sort of example first. So we have our Pythagorean identity. We naturally want to apply it to this example. So we know that the cosine of the angle is negative 2 over 3, and we know that the tangent of the angle is positive. And the question is asking us to find the sine, and also the tangent. So remember that, again, the tangent is sine over cosine. So if we know what cosine is, which we know, and if we figure out what sine is, then we get what tangent is for free. So our focus should be, to begin with, finding what the sine of the angle is. Now we know what the Pythagorean identity is. Let's apply it immediately. I mean, sine squared plus cosine squared is 1. Let's write this: sine squared theta plus cosine theta is identical to 1, or in this case for a specific angle it's equal to 1. But we know that cosine is negative 2 over 3, so cosine squared is going to be 4 over 9. We're just plugging this in. Well, now we can almost solve for sine if we subtract 4 over 9 from both sides and take the square root. Well, we almost know what it is. I mean, you think of it being, well, this is going to be 5 over 9, so take the square root would be the square root of 5 divided by 3. And it's almost this, except since we're taking the square root, we don't know whether it was positive or negative to begin with. So what we actually need to do is we need to figure out from this information given whether sine of this angle is positive or negative. And the way we can do this is using the graphs, using what we studied in the last lecture. So I'm going to draw a very sort of brief couple of diagrams, and I'm going to mark some. This is going to be pi over 2, pi, 3 pi over 2. And you'll see why I'm doing this in a moment. So if I draw sine up here, remember sine goes from 0 up to 1, down back to 0, then down to negative 1, then up to 0. The cosine starts at 1 and it goes down. It goes here, then it goes up, and then it goes up again. And the tangent sort of goes up all the way to positive infinity and then zips down to negative infinity and sort of does this. So I hope you can remember that from the previous video. Well, we know that the cosine is negative. Okay, so this is the cosine. So if it's negative, our angle must be within this region. Okay? And we know that the tangent is positive, so since the tangent is positive, our angle must also be within these two regions. Because notice that the red line is above the x-axis, therefore it's positive. Well, what does that mean? If it's in these two regions, then it must be in this region, right? It must be over here. Well, if it's over here, notice how the sine function goes below 0. So that means the sine function is negative. And since the sine function is negative, we know that it's not positive, so we can eliminate this case. And so we get the exact value of sine, which is negative the square root of 5 divided by 3. And since we know what sine and cosine are, well, the tangent of this angle, it's been a while since I've written with a mouse, so my handwriting's terrible. But yeah, this is just sine divided by cosine. And this is simply negative the square root of 5 over 3 divided by negative 2 over 3. And we can simplify this by cancelling the negatives and also cancelling the 3's. And this gives us the square root of 5 over 2. And so these are kind of our two answers, if you will. So yeah, this is just another example why our graphing section was useful, but also why we can use this Pythagorean identity, or rather how we can use it. Let's do the next question below, which I was going to hold off on the proof questions until the next, like the angle sum identities, but realistically and truthfully, the earlier the better. And so proof questions are a little bit awkward, because you've got to know how you prove it, what is the layout. And the best way I like to think about doing is you pick one of these sides. You want to show that left-hand side here is identical to the right-hand side, and this is for all angles. In fact, I don't think it's for all angles because this has to be defined, right? Because 1 over sec is 1 over cosine the angle squared, and we don't want to be dividing by 0. So in actual fact, such that the angle is between negative infinity and infinity, but we also want the cosine to not equal 0, so that this is well defined. And for all the avid watchers, if you want a quick exercise, what are the values of theta such that cosine equals 0? And those are precisely the values of theta that you don't allow. But I digress. So with this proof question, we want to pick a side and then manipulate it into the other side. So I like to pick the most complicated looking side. So this is the left-hand side, so I'll abbreviate to LHS. And this is tan squared of theta plus 1. Well, tan squared is simply sort of sine over cosine all squared, which is exactly sine squared over cos squared. And then we're plussing this 1. Well, if we want to add two fractions together, we want to make a common denominator. So realistically and truthfully, we want to add cosine squared divided by cosine squared. Right? Because it's one thing divided by itself. So this is just 1, but now we have a common denominator. And now we can add them together quite nicely. We have sort of sine squared plus cosine squared, all divided by cosine squared. Well, we just did the Pythagorean identity, right? That sine squared plus cosine squared is identical to 1. In fact, these are identities, so. Well, since sine squared plus cosine squared is identical to 1, we have that all of this is identical to 1 over cosine squared theta. And this is just precisely sec squared theta by definition, right? Because this is 1 over cos all squared, and 1 over cos is the secant. So this is just the secant squared. And this is, to sort of end our proof, this is the right-hand side. So we've just shown that the left-hand side equals the right-hand side, so we can end it there. So those are two nice applications of the Pythagorean identity. One which is a proof question, we'll do another one in a moment, and the other one is a more find a value. So now we get to what I think of as sort of the most important trig identity. And it's actually, if you have a trig function where you're adding two angles in your argument, then we can actually describe this as a product of trig functions of each angle by themselves. So where does this come from? Why is this true? We know the Pythagorean is true because, well, we can just use the Pythagorean theorem. But why is this true? And I'm going to draw this little sketch here. This is sort of, you can think of this as a rectangle. And inside I've sort of drawn this right triangle with a hypotenuse of 1. And I've labeled these sides. Yeah. So how do we do this? So how do we show this? Well, let's just start kind of describing sides in terms of our angles. Well, we know that this side here is going to be, I think this is going to be sine of phi. Whereas this side here is going to be cosine of phi. Okay, that's going to be our length. In fact, normally this would be the hypotenuse times sine of phi, but our hypotenuse is 1, so this just is the sine of phi. Well, now we can look at this triangle. And so our hypotenuse is cosine, so this length here, this lovely important length, is going to be the sine of theta times the cosine of phi. And what about this length here? This length is going to be the cosine of theta times the cosine of phi. Does that make sense? Because it's going to be kind of cosine of the angle times the hypotenuse. So we got what these two lengths are. Well, now what do we do? Well, we want to find this side. Well, we know that that length is sine. Well, what is this? This is what's the, just FYI, I'm doing all of this live, so I'm gonna have a little think. So we can so here what have we got? We've got two parallel lines, and we've got one of these lines going through. So we know that these two angles are are they alternate? Yeah. These two angles are alternate angles. So this will also be phi plus theta, right? Because this angle here is phi plus theta, and so this angle here is phi plus theta. Well, what does that mean? Well, it means that this length here, if we look at this length, well, this is going to be the hypotenuse times the sine of phi plus theta. Whereas this length here is going to be the hypotenuse, which is 1 times the cosine of phi plus theta. Can you see where this is sort of going? How we're slowly getting closer to these identities. And so the final thing to really look at is, if you look at the angles along this line, we want to find this angle so we can learn about this triangle. Well, this angle here is going to be 90 subtract phi, because then the interior angles of this triangle sum to 180. And if we add these things together, so angles along the whole line is 180, well, 180 is going to equal all of these angles. Let's call this x for now. That's going to equal phi plus theta plus 90 minus phi, and then plus x. We'll notice how these two phi's cancel, and so if we subtract 90 from both sides, we get 90 minus, and yeah, we can subtract this from both sides, so we get 90 minus theta equals x. So this angle here, which we called x, is precisely 90 minus theta. Or we can look at this and go, well, this is then theta, because the interior angles of this triangle add to 180, so that's going to be 180 plus 90 plus 90 minus theta plus theta. Yeah. So this length here is sine of phi, so this is the hypotenuse. Well, that means that this length here is going to be the hypotenuse, which is sine of phi, times sine of theta. And finally, this length here, if I rub these out, this length here is going to be the hypotenuse, which is sine of phi, times cosine of theta. And that's where this is coming from. Why? Well, we just compare. We know that this side is going to be the same as this side. Well, what does that mean? Well, that means that sine of phi plus theta is equal to sine of phi plus cos of theta plus sine of theta plus cos of phi. And that gives us the first equation, right? Because these two sides are equal. Let's compare the top and the bottom sides. Well, we know that cos of theta times cos of phi equals cos of phi plus theta plus sine of phi plus times sine of theta. So if we subtract this from both sides, we get precisely this. We get cos of theta plus phi is identical to cos of theta cos of phi minus sine of theta sine of phi. I think I mentioned in one of the earlier videos that this is sort of a diagrammatic justification. It's not a proof per se, unless we can somehow give an additional argument to say that we can do this for any angles phi and theta, because in this diagram we've chosen specific values, right? We could measure this. We can measure these angles, and so in order to actually give a proper diagrammatic proof, we need to draw pictures for every single situation, which doesn't work. But it gives a justification as to where these formulas come from. And so I've got some more proofy questions. These first ones, I might do the top one, and I'll leave it to you to check if these are true, but it's a direct application of these. So if we look at the first one, sine of 2 theta, well, sine of 2 theta is equal to sine of theta plus sine of theta. And so we can apply this equation up here. Sine of theta plus sine of theta, well, it's going to be sine of theta times cos of theta. And then we're going to be plussing cos of theta plus sine of theta. And this is by the identity we just proved. In fact, this is going to be identical. And it's identical because this is true for all values of, well, in this case, theta. If we drew an equal symbol, that means we might be setting them equal and we're trying to find a particular value of theta. So identical and equal aren't the same. But look at this. These two are just the same value, except we've commuted over multiplication. So we can just simplify this, which is 2 sine of theta times cos of theta. And what do you know? We've just proven our identity. So in this proofy question, instead of, where did I do the previous proof? Yeah, instead of starting with the left-hand side and then manipulating to the right-hand side, what I've done is I've taken a result we know to be true, and then I've just creatively picked values of our inputs such that another formula pops out. So in fact, we can, if we wanted to here, we know that something is true. We know that the sine of theta plus cosine of theta is identical to 1. So this is something we know is true. Well, if we divide through by cosine, or cosine squared of theta, so this equality still holds. We're just dividing through by cosine squared of theta. Well, what do you get? Well, this is tan squared of theta. This is just something divided by itself, so it's 1. And this is identical to, again, it's the secant squared of theta. So this works too. We can just divide through this identity that we know by cosine squared of theta, and we get this. And this is another valid way of proving this identity. So we've proven this one. I'm going to leave part 2 for you guys to prove. And so here we're going to be doing a second justification. So not second justification, a second example. And yeah, so I'm going to do what we did the first time. And that's instead of starting something which we know, I'm going to start with one of the left and right hand side. So I'm going to start with the left hand side. So this is equal to, I'm just going to write it out for the moment, you'll see why in a bit, 1 plus cos of theta. Now how do we manipulate this? This is quite it's a non-obvious manipulation. And the trick which we're going to employ, if you've ever worked with surds, say we want to simplify 1 over 1 minus 2, in fact 1 plus 2, let's say. Well, you rationalize the denominator by multiplying by the conjugate. So this is just one thing divided by itself. So effectively, we're just multiplying by 1. So it doesn't change the value of this fraction. But what happens is the top stays the same. So this is just 1 minus the square root of 2 because it's 1 times 1 minus the square root of 2. But the bottom, notice how if we expand this multiplication, we're going to have 1 times 1, which is 1. We're going to have plus the square root of 2, but here we're also going to be minusing the square root of 2. So that cancels, and then we get 1 minus the square root of 2 all squared. Well, this is just 1 minus the square root of 2 divided by minus 1, and so this is simply just the square root of 2 minus 1. So this fraction here is equal to the square root of 2 minus 1. So we've rationalized the denominator. And we're going to employ a similar trick here, where we're going to multiply by 1, but the way we express 1 is 1 minus cos of theta divided by 1 minus cos of theta. Why are we going to do this? You'll see why in a second. I'm going to multiply the top. I'm not going to expand. I'm just going to say that there is a multiplication by putting things in brackets. But if I multiply the denominator in the exact same sense where we have 1 minus this thing squared, here we're going to get 1 minus cos squared. And the reason we've done this is because if we look at the Pythagorean theorem, which is here, notice how if we subtract cos squared from both sides, we get that sine squared of theta is identical to 1 minus cos squared of theta. But when we look down here, we have 1 minus cos squared of theta. So this is quite literally sine of theta, 1 minus cos squared of theta, 1 minus cos of theta. But now we know that the denominator, using the Pythagorean identity, is sine squared of theta. Well, the sines cancel, and you're left with 1 minus cos of theta divided by sine of theta. And this is the right-hand side, and we're done. We've taken the left-hand side, we've employed these sort of tricks which doesn't change our equality, or identical, doesn't change our identity, and we've shown that the left-hand side equals the right-hand side, and so we're done. So again, this is sort of algebra because we're showing certain forms of functions for any input are equal to another form. And we can actually employ these identities to figure out specific values in a creative way. We'll do an example of that soon, but just to give you a taste of what these sorts of problems can look like. So in the previous video, we looked at periods and symmetries and recall the graphs of sine, cosine, and tangent. And we observed a few symmetries in the previous video. We observed that these functions repeat. This repeats every 2 pi, so remember that this is sort of, this point here is 2 pi, this point here is 0, and this point here is 4 pi, and this point over here is minus 2 pi. And so every kind of 2 pi units you go along, this pattern repeats. Similarly here it repeats, and here it repeats every 1 pi. And so we can describe this as an identity. We can describe the fact that if we take sine of an angle plus 2 pi, so if we take this, I don't know, this particular value here, so this is cosine, and we add 2 pi, which takes us here, it's the exact same height, it's the exact same value of our trig function. So they're equal, and this is true for all values, so we have that, we have this kind of periodic property. That's what we're saying when a function repeats every 2 pi units. We're saying it's periodic, or just any length, that is. We also have a translation symmetry. So what this is saying is it's saying that if we take sine and we shift it pi over 2 units to the left, remember if you plus something to the argument, that translates the function to the left. And so if I kind of take this and take sine here, right? And if we take this and we shift it 2 pi units to the left, notice how, even though I've drawn this quite crudely, the graphs line up. And so what this is saying is it's saying that if you take sine, shift it pi over 2 units to the left, you get cosine. And this is true for all angles, and so we get this identity as well. You often see this in other forms as well. I don't know, cos of you can often see things like, I don't know, cos of pi minus 2 subtract theta is sine of theta. This is another way you quite commonly see it. And I don't think this is as intuitive in terms of translations, but you can sort of see it. I mean, if you subtract the inputs, pi over 2 from both inputs, and you get cos of theta minus pi over 2. But as we notice now down here, we say a function is even if you negate the input, it stays the same, and a function is odd if you negate the input and it changes sign. So this is what it looks like graphically. If it's even, it reflects over this y-axis. If it's odd, it sort of reflects over the y-axis, but then reflects over the x-axis. And we notice that sine is odd, so this identity holds, and cosine is even. If we look at this, if we subtract pi over 2 from the inputs and we get cos of theta, take away pi over 2, well, we can then negate the input, and that gives us cos of theta. That cos of pi over 2 to subtract theta equals sine of theta. So if you see the identity like this, it's the exact same thing here. And yeah, we can see this because cosine reflects over this y-axis, whereas sine sort of reflects once. It reflects once to give us this, and then it reflects again. So this means sine is an odd function. Okay, and so here I'm just sort of spamming identities at this point, but we can kind of like use this, or our knowledge of sine and cosine, to look at the symmetries of these functions. Now, I mean, for tan, you can look at the graph, and again, you notice how if you reflect it once, and then if you reflect it again, you end up back on itself. So this suggests that it's odd because it has this symmetry. But another way to show it is tan of negative theta. So we're trying to show that this is either the function itself or negative the function itself. Well, this is equal to sine of negative theta divided by cosine of negative theta, because the tangent is just sine over cosine. Well, we know that sine is an odd function, so this gives us minus sine of theta. And we know that cos is an even function, so this gives us just cos of theta. In fact, these are identities. Well, this is precisely minus the tangent. And so what this means is that tangent is an odd function. And I advise you to have a look at these other examples and try and work through yourself. This one may be a bit tricky. Let's do that one now. I mean, this video is probably going to be about an hour and a half long anyway, so we look at this example. Well, let's just call this, for the sake of the moment, f of theta, because this is all one function. So, well, what's f of minus theta? Well, this is just sine of negative theta plus cos of negative theta, right? I'm just swapping out their arguments. Well, we can use the property of sine, because sine is an odd function, so we can pull out this negative. And we can use the property of cosine, because cosine is an even function, that we just sort of ignore the negative. But this doesn't equal any of our, it doesn't equal this, and it certainly doesn't equal or isn't identical to minus. Yes, because sort of we have a negative here, we don't have a negative there, but if we negate it, there's going to be minus sign minus cosine when we get plus cosine, so it's not identical either. Now you may argue, well, okay, maybe they don't look the same, the forms may not be the same, but perhaps they are still equal for all possible values. And so to actually prove that this isn't even or odd, that it is neither, to actually prove that, you prove it via counterexample. And the counterexample is to take this expression and find a value of theta such that this expression is neither positive or negative. So this expression doesn't equal this and doesn't equal that. So if we pick pi over 4, so theta equals pi over 4, well, f of minus pi over 4 is going to be negative sine over pi over 4, which I believe is the negative square root over 2, and cos of pi over 4 is plus square root of 2 over 2, which is 0. But, so we can show that this is 0, right? F of negative theta is equal to 0 when theta is pi over 4. Well, f of pi over 4 is simply sine of pi over 4, which is pi over 2. Sorry, not pi over 2, square root of 2 over 2. And then we want to plus cos of pi over 4, which is square root of 2 over 2. And so this is simply going to equal the square root of 2. So this would equal the square root of 2. And similarly, this would equal negative square root of 2. And so we know that this function cannot equal this function or this function, because when you evaluate this function at theta equals pi over 4, this equals 0, whereas this equals negative square root of 2, and this equals positive square root of 2. So they can't be equal. We found a value or an input value of which these functions are not equal, so they cannot be identical because there exists an input where they're not equal. I'll butcher that a little bit more, but I hope you can kind of see that if you just plug in this, you can show that neither these definitions apply, and so because of that, it's neither even or odd. But this is still an interesting function to look at. And the reason for that is we can actually still, it still has this shape. I mean, all of these sort of functions have this, like, well, most of the cosine functions, etc., have this nice sort of wavy shape. It's reminiscent of a sound wave, if you will. And it turns out that this sort of, when you add trig functions together, as well as sort of adding their arguments and giving you this nice sort of, we're studying, so here we've studied adding arguments. Here we're studying shifting arguments and whatnot, and negating arguments. But now we're looking at adding trig functions together. So this is the operation now which we're studying. I said at the beginning that algebra is kind of objects and properties of operations of those objects. So here now our operation is kind of adding or subtracting, if you will. And so we have this nice, it turns out when you add sines and cosines with the same frequency, so this sort of means that the same input, I guess, you get another sine and cosine wave. So this is sort of closed under addition, if you will. And we have this, yeah. So the first sort of example which we can look at is graph this function here. We'll look at why this is true in a moment. But notice how this is of this form, or this a is 1 and b is 1. And so what we want to do is we want to find what r is and we want to find what alpha is. Okay. Well, here r squared, we don't know what this is yet, and this is equal to 1 squared plus 1 squared, which is just 2. And r equals the square root of 2. In fact, I should really mention that here r is positive, or non-negative. So here r is the square root of 2. Now we can look at what is our tangent? Well, our tangent of alpha equals b over a, which is just 1 over 1, so that equals 1. And so alpha equals, I believe alpha equals the square root of 2 over 2. No. It will equal pi over 4. That's me trying to memorize my trig identities. And so what does this mean? Well, it means that y, which is equal to sine of x plus cosine of x, well, this addition is also equal to the square root of 2 times sine of x, but now we're going to shift it by pi over 4 radians. So this is quite interesting. If you add two trig functions together, which has the same frequency, and two sine and cosine functions together, you still get within you still get a nice behaved function. In fact, if we graph this, I'll leave it to you guys to justify that this is what the graph looks like. It's transformations of functions, but it still looks like this. Right, where the maximum of the height, and the maximum of the height is about here, say, and so that's the square root of 2, and the minimum goes to the minus the square root of 2. And here we've sort of shifted it along to the left by pi over 4 units. So this is minus pi over 4, and this is plus pi over 4. And this kind of, we gave this weird looking argument here that this expression is neither even or odd, but we can now look at the graph. I mean, remember that our graphical intuition is if it's even, then it's a reflection. Well, this definitely isn't a reflection, because a reflection would look something like this. So they definitely don't overlap. But also, an odd would be a reflection followed by another reflection. So a reflection on the y, then a reflection about the x. And again, if we reflected about the x, then this would look like this. Again, it doesn't look the same. It's probably a poor diagram, but I digress. You can test it yourself. If you reflect it and then reflect it again, it's neither even or odd. So we can do a brief sort of justification as to why this is true. It's like the harmonic form of a harmonic identity, I guess. And the way we sort of do this is we compare this expression R, so we compare the expression with the right-hand side. And we can split this up using our double angle formula, which is a formula we proved above here. I believe it's this one. So we prove our double angle formula. So we apply it here. We have a double angle formula of sine, so we can just sort of, and we can compare it to the left-hand side. And notice how in this case we have sort of sine x, and cos x, cos x. So for these two to be equal, we need a to be equal to r cos alpha and b to equal r sine alpha. Well, if we want to solve for r and alpha in terms of b and a, if we square both and add them together, so a squared plus b squared, well, this is going to equal r squared cosine squared alpha plus r squared sine squared alpha. We can pull out the r squared, and we get the Pythagorean identity. This is equal to 1. And so this gives us r squared. So we get the first bit of our theorem, if you will, that r squared equals a squared plus b squared. And if we want to solve for alpha, well, we can divide. We take these and we just divide one by the other, b divided by a, because this will cancel the r's, right? If we divide, this will cancel the r's, and so we're left with sine of alpha divided by cosine of alpha. And so b divided by a equals tan of alpha, which means if we take the inverse tangent of both sides, we get that kind of alpha is equal to the inverse tangent of b over a. And so this justifies what's going on. If these two are equal, then we get these two sort of situations. Now, I noted that they need to be the same argument. We can't, if, for example, we had a 2 in front of here, we get this weird looking curve. It's not going to be some shift in multiple of a sine wave, because it's not sort of, it has multiple bumps. It's not just uniformly going up and down. It goes sort of down a lot and up a lot and then down a little bit and up a little bit. So this is not a sine or a cosine wave. Okay. So we're nearing the end of this talk. So the product sum identities are something I'm going to cover, but quite often I feel like we're reaching a point where we're looking at identities which can be derived from other identities. Normally we just want new information which we can then use to solve problems. This allows us to solve specific kind of problems, but nothing really new. We could already apply our tools above. But they're important to know, because if you ever look up product sum identities of the trigonometric functions, it can look quite confusing as to where these come from. And again, just like what I wrote above, you can sort of justify using the double angle formula. But yeah, so with the double angle formula, which we proved at the very beginning, well, we got the Pythagorean identity, but this is sort of like, how do trig functions behave when you look at the double angles? So if you add their arguments together. Then we looked at what it was like when you sort of pick different arguments. Then we looked at what it's like when we add the trig functions together. And so now we're looking at what it's like when we multiply the trig functions together. So again, it's all about this, looking at the trig functions and operations which we can apply to trig functions. So we can change the arguments, we can add them together, we can multiply them together. And so we have all these formulas. Why are they true? Well, I'm not going to go through all of them, but we can look at a couple. You can look at, let's say, 1 and 5, because there's a nice duality between these as well. So how do we justify this first one? Well, I see sine of alpha plus beta and sine of alpha minus beta, and we can apply this double angle formula. So this is just stating what the double angle formula is. Here we've applied the double angle formula, but noting that cosine is a positive function, so that we can just ignore that negative. Sine, however, is a negative function. Sorry, cos is an even function. Sine is an odd function, so we can just ignore this. So we have to pull out the negative to the front. And so we get this expression. And if we add them together, notice how if we add these together, those two things cancel, and we're left with sine of alpha cos of beta plus sine of alpha cos of beta. So if we add them together, we get this. We divide both sides by 2, we get this first identity, sine of alpha cos of beta times 1/2, and then these two things together. And that's how you prove this, like number 1. And the reason why I said there's sort of a duality is we can kind of use this formula to prove the fifth one. Right? If we let A equal alpha plus beta, so notice how in this situation we have a product over here, whereas we have a sum and we have a sum over here, but the arguments here become simpler and the arguments over here become more complicated. So we're essentially swapping things around. So if we let A equal alpha plus beta, so that these things match up, that matches up with this. So this is A, let's say, and this is B. If we call A alpha plus beta, and then B alpha minus beta, we can solve for alpha and beta in terms of A and B. We can plug them into identity above. So we're just plugging them naively into identity. Those simplify quite nicely. And then if we multiply by 2, then we get the identity as we want. Did I skip an example somewhere? I don't think I did. No, I don't think I have done. Okay. So yeah, we've proven this identity. And so the final thing I want to do in this talk, which I think was super interesting and something I learnt from doing these talks, was when I was talking about the sine law and the cosine law. someone asked, is there a tangent law? And I believe you can actually go back and check in the video that I didn't think there was one because I'd never heard of one. But I didn't dismiss the possibility that one existed. It turns out that there is a oh wait, no. That's the example I thought we missed. Well, I'll look at that in a moment. It turns out that there is a tangent law. And this is the tangent law. Right? If you have any triangle with these sides and angles, then this identity holds. Now, the reason why you don't really learn about the tangent law, or I've written as the tangent rule in school, is because look at it. It equates the idea of knowing two sides and knowing two angles, which is the same as the sine rule. If you look here again, the sine rule, if we have two sides and we have two angles, then we can kind of do this manipulation where we solve for one and then we can figure out the rest of the sides and angles of a triangle. So we're not really getting anything new by knowing this tangent law. I just thought it'd be an interesting thing to bring up because I'd never heard of it before. And we can actually use this machinery about the product sum identities to prove this tangent law. Tangent rule. And we do it with the sine law. Sine law says that for kind of this identity holds, so we have kind of given this triangle. We know that this side divided by sine of x is the same as sort of this side divided by sine of y. I'm going to call this value d, so d is equal to this, and d is also equal to this by transitivity. And so we can solve for a, we can just multiply both sides by sine of x, and similarly we can solve for b. And we can just evaluate what this is. So a minus b divided by a plus b, what gives us this hefty looking expression. We can divide all sides by d and simplify, and gives us this. Well, we know what the numerator is because we have a formula above, this one. And we know what the denominator is because we have this formula here. So we can apply our addition formula and get this sort of product formula. Again, we can sort of simplify by just cancelling the 2's. And we can rewrite this a little bit to be a tad more interesting. What do I mean by this? Well, notice how this is the same as this thing divided by this thing. A little bit of algebra. But this is precisely tan of 1/2 x minus y. And this is precisely tan of 1/2 x plus y. And so we get this expression here. And this is the tangent law, right? A minus b divided by a plus b, and this is equal to this horrible looking sort of tan of 1/2 x minus y divided by tan of 1/2 x plus y. And so this identity holds for any triangle. So it's quite cool. I think it was quite nice. It's, again, responding to a question that was asked in a previous session. But yeah, so we will finish off this talk. I don't know why. I forgot that was there. Yeah, ignore the outline of a cat. Yeah, so we'll finish this talk with this example. So to show that, we're going to find a double angle formula for the tangent in terms of sines and cosines. And using this, we're going to find the exact value of tan of 52.5 degrees. So I'm just getting ready to know what the shortcut is for the keys for OBS, but I digress. So how do we prove this? Well, I typically, again, I start with the most complicated looking side, in which case we're looking at the right hand side. So the right hand side is here. And this is going to equal this, right? But if we look at our kind of identity here, so we're adding sort of two signs together. Here we're adding two signs together. So in this case, alpha is equal to 2x and beta is equal to 2y. So when you apply the identity which we've just proven, we get kind of 2 sine of, well, let's write it out in full, 2x plus 2y divided by 2. and we get a cosine of 2x minus 2y over 2. So this is the numerator. And we have a similar formula for the denominator. Again, it's 2 cosine of 2x plus 2y divided by 2. And multiplied by cos of 2x minus 2y divided by 2. And again, the way I get this sort of identity is simply by applying these formulas, in fact, specifically these two up here to the situation. Well, we can simplify, right? Because these two cancel, this cancels, and so what we're left with is sine of this argument divided by cos of this argument, which gives us tangent of this argument. And this is going to give us the tangent of, 2x plus 2y divided by 2 is simply tan of x plus y, and this is equal to the left-hand side. So we've shown that the right-hand side is identical to the left-hand side. And so this, we've shown the identity is true. And then the question wants us to find the exact value of tangent, 52.5. So this is actually quite a difficult question, but when you think about the fact that we've just shown this identity with double angle, it might be good to try and split this argument up into a sum of two things that we know. And typically when it comes to the sine functions and the cosine functions, we can use our sort of 30, 60, 90 triangles, or the 45 triangle. 45, 45, 90 triangle to find exact values of sine of 30, sine of 60, sine of 45, sine of 90, and all of these nice ones. So we really want to split this input as to a sum of two of these nice angles. And so what I'm going to look at, and you'll see why in a moment, is I'm going to look at tan of 30 plus 22.5. So here x is 30, y is 22.5. Well, using the identity we've just proven, let's just plug these things in. Well, x is 30, so 2 times x is 60. Y is 22.5. So this is just going to be sine of 45. And similarly, we're going to get cos of 60 plus cos of 45, and now we have our trig functions, our standard sort of sine and cosine, and we're finding the exact value of this expression, but we know what the exact value of sine of 60 is, sine of 45, cos of 60, cos of 45. I mean, I think I have them pretty much memorized, but if you're still unsure, remember our two triangles. We have kind of this one here, where we have 90, 60 and 30, and I believe this is going to be 1, this is going to be 2, and this is going to be square root of 3. And we also have our 45 triangle, so that's going to be 45, this is going to be 45, and remember this from the first video, so this is going to be 1, 1, square root of 2, and we can use these two right triangles to figure out what these values are. So in this case, sine of 60, so this is sine of 60, is going to be opposite divided by hypotenuse. Well, the opposite is the square root of 3, and divided by the hypotenuse is over 2. So this is just going to be, I don't know why I've done identity here, not identical because it's for a specific value. So this is going to be the square root of 3 over 2. This hits sine of 40, so if we go here, sine of 40 is going to be opposite divided by hypotenuse. This is going to be 1 over the square root of 2. Or if you multiply both sides by top and bottom by square root of 2, you get square root of 2 over 2. And similarly, if we go to cos of 60, this is going to be 1 over 2, because it's adjacent divided by hypotenuse. And here, cos of 45 is going to be adjacent, which is 1 over square root of 2, or the square root of 2 over 2. They're both equal. And so we can manipulate things a little bit. We can cancel the 2's. We can rationalize the denominator as I explained above. I think quite far up actually. Here we go, like an example of rationalizing the denominator. And yeah, going through just the simplifications, I believe the exact value, I'm going to do this in a different color, is going to be the square root of 6 plus 2 minus the square root of 3 minus the square root of 2. And that's the exact value of tan of 52.5 degrees. And yes, so that basically ends this talk. Again, what we looked at was a taster at some of the algebra you can do with trig functions. And what I mean by that precisely is we can study our mathematical objects being the trig functions, and we can study how they behave with certain operations, such as addition, subtraction, and in this case it's addition of the arguments, so the angles, but also addition of the trig functions themselves. But we can also look at multiplication and division. And it turns out there's a lot of really nice structure and symmetry which can be studied. And yeah, so I think that concludes everything I want to talk about in terms of trigonometry. If there are any questions, please ask away in the comment section. These videos are basically a talk I gave in a Discord group to a bunch of, well, some high schoolers, some younger people, so I've tried to make some of the earlier videos have some content accessible to them, but also some older students who have started university, and to them I wanted to give some interesting background and intuition. So yeah, thank you for watching.